Now let's begin our today's this morning's third lecture by Professor Xifeng, yeah, from the University of California, yeah, it's Santa Barbara. Welcome.
Thank you for inviting me. It is my great pleasure to be here to know so many young people here, and I feel it is my honor. Today, my main topic is guiding large language model via small ones. But when I look at the talk, I found that many people are interested in AI for science. So I will leave 15 minutes to talk about my recent thinking about how can we use large language model for material science discovery. This is just very brand new thinking about this area, and there are huge opportunities inside. I think we don't need to emphasize the success of large language model, as you probably have used the ChatGPT a lot, try to improve writing, try to get ideas, try to write emails, etc. And we already witnessed that the influence of this large language model has crossed the domains to computer vision, time series analysis, multimodal data, and nowadays for scientific discovery. However, as we know that every day we have new data, right? And if you are doing scientific research, you probably have lab research notes, record your new discovery. Probably you develop a new draft, like a paper draft, try to come up with new ideas and deliver the result to the public. So every day we see more and more research papers in many, many different domains. And the question is, how can we leverage the ever-growing domain-specific data so that we can get a new insight from that? And the same topic also exists in other areas, like in business domains, the companies, always you will see the new data. The question is, how can we leverage the new data and together with the existing large language model to improve the performance and to improve the quality of the result? As you can see that one straightforward solution is just to do the retraining, right? I have a large set of training data set. Now I have a new data set. I just combine them together, retrain the model. But certainly it is expensive. And in many cases, it's impossible. Like certainly you cannot know the parameters in OpenAI ChatGPT models and retrain it, right? But you also can buy service from OpenAI, try to do the fine tuning. For example, you can send your domain-specific data to OpenAI, try to fine-tune the model and get a domain-specific model for you. But again, it will cause a lot of issues, like a data privacy issue, and sometimes you really don't want to share any of your customer data with OpenAI. And it's also time issue, right? It takes some time to get it trained, especially when the data is very large. And it's very costly, right? And I know that the training probably will not take much time, but once you want to use those models to the inference, the cost will dramatically increase. So researchers have studied this problem and developed many different approaches to solve this issue. The one approach is a kind of adaptation method. Instead of try to train or fine-tune the entire parameter space in the neural network, you probably can fix like a large set of parameters, only try to tune a subset of parameters. By doing that, you actually can reduce the cost and make the training fine-tuning quite fast. There are many methods in this domain, like a prefix-based method, adaptive-based method, and LoRa. LoRa becomes very popular if you want to do the fine-tuning to come up with a new model that can accommodate new data. However, again, this is expensive, and in many cases, you need to have those parameters available, right? And it's very hard for you to get those large language model parameters in your hand, and at the same time, you freeze those parameters and you train a new model. In many cases, it's impossible. And there's other approaches, like in context learning. Basically, suppose you have a few supervised data points, like labeled data points. And basically, you can select a few data points and send to those large language model as a kind of in context learning, like a prompt. And then you can ask large language model to process new data to generate a new label. So this is quite a popular method in context learning. And if you don't have supervised data, suppose just you have some unsupervised data, a bunch of data available, what you can do is you also can rely on the retrieval augmented generation method called RAG. Basically, you have a question, and you can send the question to the retriever, like information retrieval engines, and retrieve a bunch of documents from these retrieval engines. And then you send those retrieval documents together with your question to a large language model. And hopefully the large language model will return some result to you. However, obviously, as you can see that there is a gap between the fine-tuning and the few-shot learning or RAG. Because in each case, you only can benefit from a few set of data points. The top K retrieval documents from the retriever, or the in context learning, you only can retrieve like a few sampled labeled data points and send it to. You are not actually using the entire domain-specific data you have. You only use a few data points you have. This definitely is not good, right? So we believe that there's a gap between fine-tuning and the few-shot learning. And to solve this problem, there's a nice solution there. And we have been looking at this problem for a while, and we see different researchers try to propose different approaches in this domain. But I can summarize all of them as like use the small models to guide large models to achieve better performance than just using the large model. So here's one example. This paper was written by a group led by Dr. Dongmei Zhang in Microsoft Research Asia. The idea is here, though you have domain-specific data here. Okay, so you probably can afford some small models, like small large language model here. You can actually train this small language model based on this domain-specific data and get a pre-trained language model. And when you have a new questions here, and instead of using the RAG, you can actually first consult your domain-specific model here and ask the domain-specific model to generate some like summarize the results. Like those results could be used to answer the questions given by the user. And then you can use this summarized knowledge together with the question and send them to large language model. Let large language model to understand the question, to understand the domain-specific knowledge generated by this domain-specific large language model, and then produce an answer. Okay. So by doing this, as you can see that you are not only rely on a small set of examples in your domain-specific data, you actually leverage the entire knowledge you learned through this domain-specific large language model. And then you can use this domain-specific large language model to answer this question based on the language understanding like power, like strength, like a capability of this large language model. So this is the basic idea. I found this idea is quite brilliant because it fills the gap between fine-tuning and few-shot learning or RAG kind of mechanism. So here is the performance kind of comparison between this method. The first one is you use, like if you have a question, like you have a question, you want to answer this question, use, for example, in their paper, use the Microsoft question forum, for example. And you can use RAG, try to retrieve a few questions related to your question, and then use those answers to answer your question. Or you can use their model, try to first generate a kind of like small cloud of knowledge. This knowledge might answer this question. However, because of the limitation of the small language model, the language model probably cannot precisely pick up, like select the right knowledge to answer the question. So once you get this small cloud, you can send this cloud together with this question to the large language model. Let large language model to decide which piece of information can be used to answer those questions. I think this is a smart idea, and the result is quite impressive. As you can see that it always achieves a better performance than the large language model only solution, like a large language model with DPR solution is RAG. And they also give this result to the users, like human beings, to select which answer is better. The answer delivered by the RAG approach and the answer delivered by the large language model together with this small language model. And as you can see that with very high probability that the users is always like prefer the large language model result. Okay, so this is one paper like we found. It's very interesting. Actually, after we develop our own method, later I will introduce it to you. But here is the observation. So when we look at the large language model, it's super powerful, like the OpenAI model. It is very good at natural language understanding, very good at natural language generation. It's very good at reasoning. But what is small language model good at? And if you are able to train the small language model based on domain-specific data, you have huge advantage. First, it's very fast, and you can easily change those parameters. And it's low cost. Basically, you can run using a few GPUs, right? You don't need to rely on super large GPUs. And although its NLU energy may not be as good as large language model, but it contains domain-specific insight for your research area and or the business domain. And using this domain-specific insight together with a large language model, probably you can generate a better answer. So this is basically what we conclude when we developed this method. And later we find the Dongmei's paper. I think that paper is very good. So this is my students' work in Microsoft research at Redmond. And the work is led by Dr. Like a few research collaborators. And the idea is similar, but we would like to go one step further. And the topic is guiding large language models via directional stimulus prompt. It's very fantastic title, but I would like to say that how can we develop a small language model to guide large language model to achieve better results? Okay. So here is the basic idea. You, for example, suppose we have a summarizing task. You are given a document, and I ask you to summarize this document. There's no way you can compete with OpenAI solution, right? And you can develop whatever small models, and if you want to deliver a better summarizing result, it's very hard because basically those large language model is much powerful and it can deliver better results. However, there are small opportunity for you to outperform OpenAI solution by using OpenAI. The idea is you can actually build a small language model. For example, instead of trying to summarize the entire article, I can build a small language model to generate some keywords and ask a large language model, when you generate a summary, please try your best to include those keywords. Okay, and train a small language model to generate those potential keywords that should be included in the summary is much easier than generating the entire summary. Okay, so this is the idea. Suppose you have a domain-specific data. In this domain-specific data, you have the document, and you have the target summary. And then you can train a small language model to generate the keywords that should be included in the summary. And once you build this kind of model, then you can use the small language model. When you give a new summary document, you can run this small language model to generate a few keywords, and then together with this new article to the OpenAI service, and then you are going to generate a better summary. Okay, so this is the basic idea, and this pipeline shows this process. Okay, yeah. So this is actually done by my students together with a researcher, Dr. Gao Jianfeng at Microsoft Research during the summer internship. But it's very good idea. So here is the process, right? So you have a summarizing task, and I use this small language model to generate a few of keywords, and then send to the black box like OpenAI ChatGPT, and then ask the ChatGPT to generate the new summary. And this summary result is usually better than you directly use the OpenAI API service to summarize the article. Okay, so there's two ways you can do the training. The first one is you can just suppose I already have some domain-specific labeled data. I have the domain-specific article, I have the domain-specific summary, and then you can use text rank to generate some common keywords existing in this document and in this summary. And then you can create a training data set between the article and the required keywords that should show up in this article. And you can use those small language model like open source language model like T5 to do the training. And once you have this, Then if you have a new article, you can generate new keywords, and then you can send to the OpenAI service. Okay, and you can do a little bit more than that. Instead of doing this kind of supervised fine-tuning, you can do this kind of reinforcement learning. So suppose you have some kind of training data set, you have article, you have a reference summary, and then you can use that process to generate a new summary, and then you can compare the difference between summary. And you would like to change your model. You would like to change the model such that the model can generate a best set of the keywords such that the generated summary will be as close as possible to your reference summary. So this is a typical reinforcement process. And by doing that, you are going to generate a better small model for generating the keywords. Just with these simple ideas, and this figure shows that you actually can outperform the OpenAI service, using OpenAI service. Okay, so here is that you directly use the ChatGPT, and this is using the supervised fine-tuning. This is use the supervised tuning together with reinforcement learning. As you can see that you can improve the performance a little bit. But this is already very hard because you are not competing with small language model. You are competing the most advanced like a large language model in the world, and it can achieve better performance. Okay, the same concept actually can be used in many domains. In the next few slides, I will show that. The first one is chain of thought, right? So some of you probably know chain of thought. Basically, the original solution of ChatGPT is you give me a question, I would like to directly generate the answer. But you know that this is not the way we generate the answer, right? When you give me a question, I will first think several steps. And after that, I will give you the answer, right? So chain of thought perfectly capture this kind of intuition. So you give me a question, I try to give you some kind of reasoning steps. No matter whether it makes sense or not, I give you something, okay? After that, I'm going to generate an answer. I give the answer to you. Okay, and the question is, in order to do that, you have to put the prompt there, right? You will ask the ChatGPT, okay, please solve this question. Please give the reasoning step by step before you arrive at this answer. Okay, so this actually is quite interesting. But when we check different prompts, it actually gives you different results. Okay, from here you also will see that actually the ChatGPT service is not that reliable, right? You give different let me do the next step. Let's think step by step, or let's think something like this. If we give different prompt to ChatGPT for the same question, it will give you different accuracy. Okay, it's quite different, right? Someone is like 60%, someone is 80%. Even you don't change your question at all. It's fully depend on your prompt. Okay, and does not depend on your question. Okay, so here what we are thinking that, okay, give me a question, which prompt could be more useful, or whether there is a new prompt we can generate by modifying those keywords a little bit, so that we can actually achieve good performance consistently. So now the idea is quite simple, right? What you can do is just do the same thing, right? You give me some kind of training data points. I train a small language model. The small language model will pick or modify which prompt you would like to use, and then send this prompt together with your question to ChatGPT and get the answer. Okay, so you could have two versions. You could have a supervised fine-tuning version, or you could have the reinforcement learning version. Basically, the idea is you are going to change the prompt in a way that hopefully the question answering accuracy will be improved. So this is the basic idea, and this is our result. And you can see clearly that just without doing any kind of new ChatGPT, okay, you do this kind of they call DSP, I call the small models to guide large models. You can achieve the accuracy achieve the accuracy 84%, and you can compare this accuracy with all these human designed prompt, and this accuracy is better than all of them. Okay, this is for one task. I think it is mathematical. This is probably algebra, and you can see that this one is better than all of them. Okay, so this just gives you a solution that if you are not able to develop a large language model and you have to rely on their service, at the same time, you want to keep your data, like you probably still share some data, but you want to keep the majority of data for yourself, and you can train a small language model by doing that, and the performance will be quite good. Okay, so one of my students look at this paper, and he started to think about it. He is from a hedge fund, and he said that, oh, why not we use this kind of thing to analyze financial news? We know that if there's a big financial news, the stock market will change dramatically, right? So yesterday, Trump picked the BP, and you can see that suddenly the Dow Jones jumped dramatically, but the Nasdaq doesn't change a lot. So from here, you can see that the news actually will have some kind of short-term influence of the company's stock value. And he's from hedge fund. He said that, okay, let's do that. Suppose we have a news like this, okay, and then we would like to predict the stock change based on this. You could have the 7 days predict, 15 days prediction, and the 30 days prediction. You are not going to predict the absolute value. You are going to predict whether there's a 5% up value or down value, something like this. And he built a model like this. And then he think sometimes we cannot just do this kind of prediction based on the current news. You have to actually retrieve the past news and combine them together to do the prediction. Here is one example. If you just want to do the prediction based on this news seems not positive, right? You are going to sell some of the company's business in order to do whatever. If you want to sell one company's business, usually it's not a positive signal, okay? But if you look at the previous news, you will see that the reason they want to sell this business is because they want to reduce their debt. Okay, probably this is not that negative news. Okay, so you have to consider all of those previous news that is related to your current news. The question is, when you consider more and more news, basically you cannot squeeze this in together with your current article to some kind of ChatGPT because it's very expensive. Second, you probably cannot do any kind of fine-tuning there. So he has some GPUs, 2 GPUs. His hedge fund is not that rich. Has 2 GPUs, A100 or something like this. And he cannot afford to do this kind of training that put all of this news together with this one and do the training. So what he can do is try to come up with a small language model to do training on this part and use large language model here and combine them together and fine-tune the method. So this actually works, okay? So you have a large model on the current news, and you have a small context encoder that summarizes the key information in the historical articles. And then you combine them together, you are going to predict the up-down on side of the stock price. Okay, so here is as a result. The result is quite good, okay? And you will, like using this method, he actually changes the Mistral code to bidirectional and add this summarization information, and he can achieve annual return 15% and any volatile like this. So Sharpe ratio is above 1. So basically it means it is tradable. It gives tradable signals. So this is done by Ross. I just have a joke with him that, okay, I mean, you cannot publish this paper, and the reviewers are going to challenge it. If it's really like make profit, basically why you publish? If you cannot make profit, why you publish? Okay. But it's interesting. But he told me that you cannot rely on single signal to do the trading. You have to rely on hundreds or more signals together to do the trading. But anyway, this just gives you an example that sometimes even we cannot have those large resources to do this kind of fine-tuning. Using the combination of small language model and large language model, you probably can still deliver something interesting. Okay. Okay, so this is just one direction. And then in parallel, actually, we are doing another things. Like we joined the Amazon Alexa social bot challenge last year. And in a very separate way, we actually also discovered that small language model actually can help large language model to do the better job. Even when we are doing this kind of challenge, we didn't recognize it. So here's the challenge, okay? So this is called a social bot challenge. The idea is they invite like 10 universities and try to each team build a social bot that can converse coherently and engagingly with humans for at least 20 minutes while achieving a user rating of at least 4. So basically, they give the user 1 to 5 rating, and the user will give us a rating, and if the average is greater than 4, that's great, okay? And Amazon promise give you $1 million if you can achieve that, okay? Turns out it is achievable because of ChatGPT. So later Amazon recognized that you cannot send the user data to OpenAI because it's break the agreement. So we are not allowed to send the real user data to Amazon in order to make these conversations. We have to develop our own small language models together with OpenAI API to achieve some kind of good performance. So here is a key issue that that we discovered when we use this leading large language models. So you actually can check ChatGPT if you are able to do the VPN to get the access. So suppose you have a user. The user is very bored Saturday night, and he opened the Alexa, like the Echo, and tried to have a conversation. So user is quite passive, and he will just say, okay, no, it's that's true, etc. Probably he's tired. And if you try ChatGPT, I always give this kind of answer. It's very boring. Okay, we observe this, and eventually the user will close the conversation. It's useless, right? So we find that ChatGPT, like those large language model, is very passive. Okay, it's not like because they are trained based on the instructions and the previous sentences, and try to predict the next sentence and next tokens. And if you don't give them very active instructions, so basically it always gives you some kind of passive solution if you don't propose some interesting topics to talk. And we actually raise a question to ChatGPT, like, please say something. The ChatGPT gave some answer like this. Certainly no one is interested in that, right? Probably some of you, but it's not interesting. The question is, okay, because a large language model is trained this way, in order to make it more active, you probably need to send something, tell it to be active. And you need to give the large language model some hint, such that it gets the hint, it can propose new topics, change topics, engage user in some way, so make the conversation more exciting. Okay, so this is what we discovered. And when we want to have a conversation with real users, and the real user seems very interested in sport, specifically basketball. So in this case, we immediately detected this user is interested in basketball. So we just send this prompt to OpenAI and ask OpenAI, please say something that relates to basketball. And then OpenAI will mention something like Stephen Curry. And when we discover that, oh, Stephen Curry is mentioning this, and probably we should just not leave this topic, right? We probably need to dig deeper into this topic, such that let's ChatGPT talk more about Stephen Curry so that the user can be engaged. So as you can see that you cannot just have a universal instruction and let the bot talk with the user in a very engaging way. You have to dynamically change those prompts during the conversation such that the user will be engaged, such that the conversation will be as long as possible. Okay, so this is our goal. Okay, so here you probably already figure out this is a standard small language model problem, right? Whenever we see this kind of conversation, how can we pick some kind of prompts and see this prompt is more appropriate for this conversation at this moment, and then send this prompt to OpenAI and let the OpenAI to generate some interesting topic so that we can continue talking with the user. Okay, so this is the basic idea, the same idea. So there are two ways to do that. One is, again, use handcrafted prompt and use small model to pick the prompt. The second way is called dynamic prompting, is more advanced. So instead of let the small model to pick the prompt, you let the small model to dynamically generate the prompt based on the trained data set, and then send to the OpenAI to get the better result. So this is the idea. So eventually, we built a system called the culture chat system. Here, I just remove a lot of details because I'm going to talk about AI for science. But basically, we have an architecture like this. We treat a language model as a promptist. So these are small language models, small language model that can be trained in my own lab where we have few GPUs there. Okay, we also can use small language model to pick a topic, right? When you have a conversation with a user, when you want to engage a user, you have to switch topic, right? After you're talking with the user for a while for a specific topic, both sides will be, and bot will not be bored, but the user will be bored, right? You have to detect at the right time and switch to a right topic so that the user will continue talking with you, right? Otherwise, the talk will end abruptly because the user has no interest to further talk with your bot. And we have also have the RAG engine, and the RAG engine is able to help us to retrieve those new exciting news from internet, right? Because we found that people always are interested in talking about new things. Older things are not that interesting. You are talking about new things, new news, new events, new like a vacation destination, etc. Okay, with all of them combined together, we achieved the #1 performance for this competition. Of course, the condition is you cannot send the user conversation to OpenAI because actually OpenAI can have quite a good conversation with the user. So here is the performance I changed. We dramatically improve the performance by introduce some kind of quite proactive prompts and send the prompts to OpenAI and get a better content for the current conversation, and so that we can engage with the user. So something like this. Okay, so it seems the problem is very universal. So I do not know. Some of you have attended a NeuroPace last year conference, and in this conference, when you have a speaker, and always display the speech recognition result here. And if you look at those video, you will see clearly that for many abbreviation like keywords, the speech recognition service cannot recognize those new words or new abbreviation very well. So basically, it means that those speech recognition models are trained on the past data. When you have a new abbreviation, new acronym, new words, they cannot recognize them. So you have two options. One option is fine-tune, retrain your model. The second option is this. You try to build a small language model and detect something, and then tell the speech recognition model, you probably need to pay attention to this new abbreviation word. I'm quite confident that using the current OpenAI techniques, with this small language model recognition, with those standard recognition from the existing model, it can come up with quite a good like speech recognized result and deliver to user. Same thing for machine translation. There are always new terms, new words, new things, and image recognition, new object. And nearly all AI tasks have this kind of phenomenon. Every day you have new data. You cannot expect that you have to rebuild the system from scratch in order to absorb this new data. You need to develop a kind of fast and low-cost solution to absorb them so that the performance can be better. Okay, so this is just to finish my first part of the talk. I hope I can deliver more, but consider the theme of the talk, I would like to share my own view about what AI can do for material science. Okay, it seems that this is the theme for today, AI for science. I will connect this part with the small language model I just discussed. So 20 years ago, I spent a lot of time to do the graph data mining and the graph net management. And you can see the chemical compound, all of them. Many of the data, scientific data can be represented as graph, okay? And we develop quite good algorithms that can help us to find the frequent structures existing in this graph data. In this graph data. And we can treat each graph as a set of features. So basically what we have done is we vectorize a graph to a feature vector. Okay, this has been done 20 years ago. Okay, and once we have these feature vectors, then we can do graph clustering, like graph classification. You try to predict the property of those chemical compounds. And you also can do the graph index, try to retrieve those chemical compounds that are similar to your structure. And we have done a lot in this domain, okay? And 20 years later, in dismay, I suddenly recognize that, okay, this area becomes hotter again because there's a professors in material science approach me that, see, hey, Xifeng, how you look at this area? Then I suddenly recognize that, oh, we actually can combine the first part of my talk together with the second part. My principal work, this is my PhD work 20 years ago. So everything is very similar, except that they have a better way to vectorize a graph into a feature vector. So Philip just talked about like how can you use a graph neural network to do this kind of prediction. Same here, you actually can use the graph neural network to do this kind of node embedding and graph embedding. And if you use a node embedding, basically this each mean one node. And you get the vector for each node. You also can add this embedding all together and get one vector. Using this one vector, you can represent this chemical compound. Okay. Once you have this, then basically you can do the graph neural network. You also can do transformer-based deep learning, try to predict the property of the graphs. But I'm not going to talk about it. I'm more interested in like what is the big picture that AI can help scientific discovery. Take material science as one example. I want to link this potential of AI for science with something like what we have discussed for a long time, level of autonomous vehicles. I would like to do a comparison between AI for science and this level of autonomous vehicles. So level 0, no any AI enhanced discovery. Everything is based on the scientist owns capability, right? Read the papers and go to the conference, come up with new ideas, do some experiment. Everything is like this. Okay, this was what we have done. But we can go to a little bit level 1. Instead of just rely on human efforts, you can rely on search engine, right? You also can rely on those scientific tools. If you want to do some calculation, there are so many packages available. For example, you can calculate the weight of a chemical compound. Okay, there's a lot of knowledge retrieval algorithm available. You can rely on the Google to get it. So this is level 1. Basically, there are some kind of tasks you don't need to do manually. Actually, you can rely on those existing tools to help you solve those questions. And level 2 is, can you do a little bit of reasoning, right? So I want to know whether this chemical compound has this property. Maybe in the literature, no one mentioned this chemical compound has a property, but maybe in the literature, a similar chemical compound existed and some experiments have been done and show it has this kind of property. Can we just do this kind of simple reasoning? It's different from retrieval, right? Retrieval, you have to be exactly the same. For this reasoning, you will find the similar structures and then you show that, okay, probably this compound have this structure. And then you can do the level 3, the property prediction. I give you a kind of chemical structure. Can you help me to predict the property? And the level 4 is more crazy. So basically, I have no idea about what structure is. I just have one structure like this. I'm not satisfied with this property. I want this structure to have this specific property. Can you help me generate a new structure? Likely it has this property. It's a kind of synthesis. It's a kind of hypothesis generation, right? You don't have this structure, but you hope that the machine can automatically help you generate this structure. And once you have level 4, you can reach level 5. Level 5 is just to have an infinite loop. You start from level 4 to get some kind of new idea, and go to level 3, try to rank those ideas to predict those property, and then you can pick a few top K, like compounds or structures or whatever, do some experiments, and then you gain new knowledge. So this is your domain-specific knowledge. In many cases, you don't want to share with others at the very beginning, but certainly in the end, you would like to, right? And then you can go to level 4 and do this for loop again. By doing that, actually, is toward autonomous materials discovery. But again, like the autonomous cars, it will not happen immediately, but we are, for these autonomous vehicles, we are closer and closer to this goal. This just starts. I think that has huge opportunity there. Let me see, one minute. Okay, so let me show you a few research work, not from my group. I just checked the internet. I see already there's a lot of work, but many of them are brand new work. It's 2024. And the first one is knowledge retrieval and tool use. So basically, you could have a question. You want to know, for example, like what is the stiffest material with the lowest formation energy in SIO system? I have no knowledge about what this question is. But using this kind of multi-agent system, you are able to decompose this query into different subqueries, and then send this query to internet, also other tools, retrieve those results, and try to figure out what is the solution, what is the answer to this question. So this can be done automatically, and of course there's errors, there's issues, but at least it helps you. Originally, you have to do this by all yourself, right? Try to do the internet, try to decompose this query, go to the internet, find some similar structures, check another tool, find the property of these structures, do some calculation. You have to do it manually, of course, you rely on. But now with these AI techniques, you can do this kind of agent kind of stuff that can help you finish it quickly. Then level 2, there are already some study. I do not mean they solve this problem, but there are already some kind of new things people are trying. Here is one question. The question is, below is a description of a Baucom material. Then you just list a formula there. Generate a description of the length and angles of the lattice vector, and then the element type and the coordinates for each atom within the lattice. The idea is you give the name of the formula. Probably this one hasn't shown up in any kind of literature, but this large language model is able to generate this structure for you. And in many cases, it's correct. Okay, so this is amazing. Okay, if you are interested, you can read those papers, but this is just started to show up. This is different from that you build your own data set. The data set collect a lot of this kind of thing and has a lot of this kind of coordinates structures. And then you train a model, and the model will just do this, predict this. It's like trying to harvest the entire literature in science, including chemistry, material science, physics, etc., and try to come up with something that can better do the better prediction. Okay, and then we come to the level 3. Level 3 is proper prediction. For example, you have a structure like this. Okay, then you want to predict what's the you want to predict some property. Okay, whatever, and then use this level 3. You give me the description of your structure, and you can predict some property, even with some accurate number there. And sometimes you can do the reverse prediction. I want to have a structure has this kind of special property, and can you automatically generate this structure? Okay, so this is a little bit harder. This is easier. Okay, this is level 3, and later you can do all these kind of thing. Level 4. This is another paper. Okay, level 4. Basically, you give me this kind of structure here, information, and then you show a prompt. And once you give me the prompt, then I can do the material generation, generate this new structure. I also can give the description of this new structure. And although I can do something that if there's a missing component in this structure, can you guess for me for this missing component? I'm not a material scientist. This is brand new to me, but I think this is one way to go. There will be more and more research papers. I do not mean for this area. There will be more and more research papers in scientific discovery. No one can read all of them. Probably you can only read 10%. And 20 years ago, later, you probably only can read 1%. Just too many papers, okay? And you have to rely on the large language models to digest and harvest the knowledge existing in those research papers. And hopefully, using this kind of method, it can assist you to discover the new knowledge. Then the question is, what's our opportunity, right? I mean, OpenAI certainly is doing this, right? Try to download all of those research papers. And fortunately, like Nature, this kind of journal allow you to download the papers now, okay, freely. And they certainly are passing those papers. But they can do that. Then what's our opportunity? So I think our opportunity is domain-specific data and knowledge. Okay. For each lab, probably you have a lot of lab notebook there, and each lab probably accumulate a lot of knowledge, and many of knowledge probably are not on the papers because papers are very serious things, right? You have a theme, you have a story, you have to conclude. But you probably have a lot of discovery. They're not that like formal. And how can we leverage those lab domain knowledge and all the newest research papers and build a kind of domain-specific models so that these domain-specific models can work with those large language models, which are very good at natural language understanding, but probably do not have the domain-specific knowledge hidden in those scientific literatures and reports. And how can we do that? And so here is one architecture called Lava, and some of you probably know. Lava is a kind of multimodal large language model. The idea is it can do the image together with text, and then you can answer a question. For example, this text is a question, and you give me an image, then I can give you an answer. Okay, so you can just start to imagine that, replace this image as a papers, right? And you have a question, and you get your answer, right? And this question could be not just a knowledge retrieval question. It could be any kind of insight or hypothesis generation question. And it will give you some new idea. So the architecture already is there. The portion we need to solve is this part. And this part need a domain-specific model, which can pass the domain-specific data you have, like a research report, etc. And then it can do some prediction. And eventually it go back to this, right? You have your own data, and certainly you do not want to send all this own data to the OpenAI, and how can you leverage it? Okay, so, and this one probably is the answer. And again, eventually we go back to our original question, that how can we have an architecture such that our own domain-specific data can coexist with those like a large language model. At the same time, we can get more insight from our domain-specific data. So this is for today's talk. I hope I successfully combined these two areas together and deliver something interesting to you. So any question?
Thank you. Thank you.
Yeah, please.
Thank you, Professor. I have a question about the first part of the get a summary from some maybe articles. It seems like the small language models only conveys some keyword to the large language models. How you make sure that the large language models get the right logic correlations between these keywords?
That's a very good question. I think we have to be very cautious to generate those keywords, right? I think the key point is there's 2 points here. When you give the prompt to large language model, you should not require the large language model. You have to include all of those keywords I suggested. You should say that this is a document we would like to summarize, and please try your best to include those keywords if you think that these keywords are related to this document summarization, and then give some freedom to the large language model to figure out what the language model really want to summarize. This is step one. But I think more important is about the reinforcement learning. The reinforcement learning itself will give the signal. If you include, if your keywords are not good, so basically the OpenAI service will give a summary that includes those keywords, but this summary might not be as good as the original summary. So if you use a reinforcement learning, you compare these two summaries, you see there's a big difference. Then you send a signal to here, let this one to adjust this keyword set a little bit so that it can generate a better summarized result. Okay, so this is the basic idea. Okay, but the performance improvement only 1% or 2%, it's not that big. But I think this is a direction that we can help, unless you join OpenAI. So otherwise, I think this is the one way you can play with it. So that's like recursive? Yeah, recursive. You can just do the reinforcement learning to do that. But we want to demonstrate that still there's space you can improve. There's a lot of researchers who are doing this document summarization. They just stop working on it because you cannot compete with OpenAI. It's just too powerful for NLU and NLG. Basically, when you do the document summarization, you need two things. You need to be very good at it. One is NLU, you need to understand the entire document. Second, NLG, right? Basically, you need to generate those sentences, new sentence, not the old sentence. Traditionally, when you do the document summarization, you just extract the sentence from this document and put them together because you don't have the vehicle to generate a brand new sentence. But ChatGPT certainly can do that, right? So though here is it's done area, but through this work we demonstrated you still have some possibility to improve that without sending all your training documents to OpenAI. Okay, thank you. Thank you for the question.
Okay, thank you. Dear Professor, I want to know that can this process be applied to other kind of structure designing, for example, the robot mechanical structure? As far as I know, some researcher group, they are just designing the new robot structure just in need of their desire. For example, picking the apples. So can this process be transmitted to that area for the robotic designing, structure designing?
I don't know whether I understand your question correctly, but let me rephrase your question. The question is whether we can use a large language model, this kind of thing, to help the robot to do better object picking or whatever, right?
Yes. Maybe not only in the robots, other area of designing or some finding the new structure, like something like this.
Definitely. I think this is a good area. I think for current OpenAI, this kind of thing that, especially for new, like there's new research area called the LM for hypothesis generation. You just generate new things, new design, right? I think that can be used. I really appreciate this conference because I took a ride with, in a bus, I talked with a professor from Maryland. He said that, I said that we would like to remove data hallucination because for business application, OpenAI, like this ChatGPT sometimes generate the wrong answer. It's a disaster for business, for company, right? You can use $1 to buy a new car and you cannot refuse it because your boss said that you can buy my car $1, right? So for this kind of thing, for business, you definitely want to eliminate it. But he said, here's a scientific research. He wanted the ChatGPT to generate more hallucinated results. Those hallucinated results actually contain new ideas, probably new design, new hypothesis. Actually, you can let the scientist to think more, think out of box, think about new things. I think this is definitely one thing you can do. So probably we should write a paper like this, more hallucination, and that's actually could be appreciated for a specific like a group of specialists. Yeah, I think it's a good question. Yes, I think it's a way to go. Yeah.
Okay, thank you.